Hi, I'm Jared Semler. This is lab number 4. First, I'm going to start off by explaining my code. So first of all, I set the variables to define sample frequency and define the delay. Then I define the serial port speed to be this number. Then I set the variables for the end scope and the potentiometer based on the analog ports that they were plugged into. So for the end scope, it's reading A1, and then for the potentiometer, it's reading A2. After that, I have this code, the serial.println, that basically is going to be sending the code over to the potentiometer. And after that, I have 4 if statements that essentially, when the potentiometer is turned to a certain point, the sampling frequency will be set to the condition of the if statement. So with that code, I was able to go ahead and begin graphing using the end scope and using processing. So I started off with f equals 75, and these are different graphics I got. Then after that, did f equals 100, and I got these for the sampling values. After that, I did f equals 215, and then for the sampling values, I've got as follows. Then lastly, I did f equals 300 and got as follows. Okay, so after that, I went ahead and filled out the table, and so our desired values were 500 hertz, 200 hertz, 142 hertz, and 100. Actual were 410, 184, 134, and 96 from the VSA. Then we went ahead and did delay per sampling time, which was these values. Then the Nyquist frequency, which is the actual value divided by 2 for each of these, and got the following values. Then for each of these, the Nyquist is going to be 75 times, the frequency times 2 of the respective ones, and then it'll be like that as continues. And then for the rest of this, I did the calculations and looked at the VSA chart to compare the alias frequency theoretical and the alias frequency experimental. And the ones where we got major differences were tending to be towards the higher frequencies. So more down here, not as much up here and here, and kind of here. Here's a quick display of my calculations for my aliases of the theoretical. So here is our square wave, and as you'll see, the frequency is represented by many different values with varying amplitudes and varying frequencies. And this is because to represent a square wave, you'll need an infinite amount of cosine and sine functions to represent this. So lastly, this is our triangle wave, and similar to the last one, you can see that there will be in the frequency and voltage domain multiple different values of frequencies with amplitudes. However, it's not infinite like the last one because it takes a smaller sum of the sine and cosine functions than the square wave did. Thank you. And finally, here is the circuit that we use throughout this entire thing. You'll see that A1 is plugged into the end scope, and that's plugged into channel 1. You'll see that A2 is plugged into the potentiometer to control, to allow for the potentiometer to control the different waves. And then the only thing that we changed for this was during the square wave demonstration, we changed A1 to P1. And that's everything.